you guys to turn in the physical packet of the Chem Activity 22. I made a link in OWL just to remind you, and then I snuck in. I was like, I got to put a link, so I'll put a link to the course schedule. I update it once a week, so that's a good place to look. It also has additional POGO activities. You have the whole PDF of all 48, 52 activities, whatever it is, so you can go look at the additional activities. It'll help you strengthen what we're doing in class. If you haven't completed the doodle polls, I'll pick a office hour and supplemental instruction times based off of that. So if you haven't given your input, it's a good chance it won't line up with your schedule. So please do that. That was an announcement that was sent out a couple days ago. The supplemental instructions will not be required. There are other things you can do, but I think it will be vastly helpful. I'll be working with a peer who has taken these courses before, who's a chem major, who will be running them, but I'll be working very closely with them, designing the activity and all kind of stuff. You can do it outside of class, but it's not going to be quite as good. So if you can make it, try to make it. So the things I wanted to talk about that are related to y'all, see, I'm fitting in, right? But not necessarily part of class, so I want to start a minute early, is if you have any interest in teaching, we as a state need teachers, especially STEM teachers. So there's a National Science Foundation grant that has been awarded to UALR. It's called the Noyce Fellowship. It gives you, it's totally noise. It gives you $10,000 a year for your junior and senior years. There is some form of commitment that you will be teaching in the state of Arkansas after that. But if you have any interest in teaching, even if you're not sure if that's what you want to do, I really, really advise you to email me. I'll put you in touch with the coordinator of that, and then they'll be happy just to chat with you about what it might look like, and then you can decide if it's something you want to do or not.
On that same note, the school system in Little Rock is always looking for substitute teachers. I'm a substitute teacher. It pays about $70 a day, and they always have STEM classes available Monday, Wednesday, Friday. So
awesome.
If you need an extra $70, it gets deposited directly in your bank account.
And it's great practice.
Yeah.
Like, that's fantastic.
I teach the chem classes, so it's really
I believe it.
extra classes, like extra practice stuff.
Fantastic. And supposedly they still have money available for this year. So if you happen to be a non-traditional student or something and you're not going to be here in 2 years, then you might still be able to get a $10K for this year, as I understand it. So let me know if you're interested in that. The second thing that's related but unrelated, it's related because there are recyclables in here. There is a water bottle, and there's some plastic down here, and I didn't even plant those. I've given our students a hard time for doing that in the past. But Arkansas is really, really bad for recycling. So there's a group of students that are out of Fayetteville who started lobbying for container deposits. So they'd go a lot into place. You'd have to pay 5 or 10 cents when you bought the bottle, additional for the bottle, and then you could get that money back when you return it. So then homeless people in cities that have these go scrounge up empty bottles. They pull them out of garbage cans. They pull them out of the river. It helps to clean up that way. It also gives people a financial incentive. So they're looking for someone at UALR to help spearhead this campus's effort. They have people all across the state at different universities and organizations. If you're interested in making an impact in the environment around here and in the state, they would be really happy to have someone. I'll be happy to be the faculty advisor, but my time's spread pretty thin, so it would need to be student-run, and then I could support it. So email me if you're interested in that. All right. Let's Poggle. Today, who do we have for our facilitators? So we have Peter and Emily, but I believe that we're also going to have 2 more in-class facilitators, learning assistants. Nabil and Josh are going to join us today. So as you have questions working through these activities, please raise your hand. We will help unstick you and move you in the right direction. For now, get in groups of 2 to 4 people and go ahead and start on activity 23. This is the most important part of the activity. Don't just skip to the problems. I see people already flipping the page. Austin, no. That's just messing. Make sure to read everything really carefully because those first 2 pages are a lot of information that you need to come back to. So please pair up with someone around you, 2 to 4 people, and start working through.
I note says every time you log in, you can buy more, but you're good for this semester.
That's funny.
And every time you click into your book, it's like,
They're really bad at that. Because as a faculty member, I still have something pops up. Faculty resources here every time I log into the first page. Dude, I never like. Can you remind me at some point when it finds down all the outside? That is. Yeah.
as you're dipping those. All there means is that it's certain levels.
It's a little arbitrary, and this kind of gets into more of that, where it starts talking about distance as well.
There's a vending machine right there.
So it's saying,
They got one in your office.
look, we found partial negative. So one left open. Then we're going to figure out where the center of the negative charge is going to be located on the mass.
But this one's supposed to be too.
Right. And that's, so that one is going to be
We're just on figure 3, and I know just so I can.
Yeah, so you're charged to do that.
I just don't understand like
That all fine.
Just putting it visual. I had to draw it, I was at least that's what
She's like pouring like this down. Come on, bro.
You can say that the force on the other side offsets force on one side offsets Exactly. Well, what if they cancel each other out? I was saying that three lines are like starting.
That's three different apps. I mean, there's three different yeah, because O and S have different
Oh, between.
Oh. Sorry, I thought we were talking about
You're talking about
Oh my gosh. That makes sense. I only lost this on. I thought it was like 8.
That's why I kept saying teaching. Okay, but you.
Because in that case, if they think that you know open sectors more towards the middle, automatically more towards the middle of the actually, the same question. I would say there's a I'll be right with you guys.
Okay, so I'm trying to figure out if the switch from the larger distance to HF or ACL, but how is it hard?
Yes.
Same thing for the CO.
I would guess, absolutely. Yes. Hi.
Hi. Okay, so each part, we have determined the
Okay, so those
I'm just trying to figure out why. So it says, which of your coworkers back to yeah. I just can't I think it's about we have
we are on the Okay, you'll be fine. I'm sure that is a deal. Not having a whole lot of conversation. So I guess you gotta refer to these right here, You're saying that after the back over the yes, I would think it is the partial charges. Right, because they're both so small. I don't expect right, but that's figuring out the way that they work. But intuitively, according to what the ice magnetism beforehand, so you get. Let's look at what we've got going on here. Looks like a dipole building here. A very large
Thanks, everybody. All right, so let's talk through some of the points you guys have already been working on to make sure we're all on the same page and for the same reason. A lot of times it's easy to, we know the answer and so we're just kind of answering it, but I want to think about the why. Okay, so question number one, can I get a volunteer? How was the center of the positive charge for the H2O molecule in figure 3 determined? Where did they come up with that positive, center of the positive? Echo?
Because it was located midway between the H atoms.
Midway between, why the H? Why is that important? They're what? Missing a word? They're the
Positive charge.
partial. Okay, so this is a really easy thing to fall into, is just say positive and negative. Why is that so wrong? Did you guys come to class last Wednesday? Some of you said or didn't, so it's okay. All right, but you've done 2 full activities on the partial charge, right? So if we're doing the calculations of the partial charges and you call it a full charge, you just ignore the last 2 activities that you did, and that's kind of sad. So does water have any charges? Any full charges? No formal charge, okay? So on that particular bond on the left side, oxygen pulls the bonded electrons a little more towards the self than the hydrogen, so it's partially negative. We could calculate that, all right? You guys did that. You could say the same thing about the other bond. And then the one thing about the activity that's not super clear on that second page is it says center of positive, and you're like, is that just like up here? Like, where is that, right? So what would be helpful is to actually, if they had like made a circle or something there, it's hard to indicate, right? So what they're saying is the center of the positive, partial positives, is here, and it's because it's between the only partial positives that exist. It's going to get more complicated, right, as you guys have seen as you work forward. They're just starting out with a simple one with two partial positives. Where's the center of the partial negatives? Austin? So I'm going to put a little plus there, a little minus there. All right. So this is the center of the partial positives that exist in this whole molecule, center of the partial negatives that exist in this whole molecule. And so the overall dipole moment of the molecule, how do we find that?
U equals G times D.
We could calculate it mathematically, but conceptually, where do we find it? How about we just connect those two? That's the fourth image in that line of diagrams, right? So they literally said center of the positive, partial positives, center of the partial negatives. We connect those two. That's how we tell if there's a dipole, and we can kind of show it graphically. What about for CO2? Can I have a new voice? Where is the center of the partial positives for CO2? I'm going to redraw this. Gives us that it's linear, so if we're a little rusty on Lewis structures, it gives us a leg up. Can I volunteer? Moab?
Partial positive?
Yeah, where's the center of the partial positives?
On carbon.
On carbon. Because those are all of our partials. So if we go back and do blue, the center of our partials is there. Manu, where's the center of all our partial negatives? Right in the middle as well. And so I can't really draw that on top. Maybe I'll draw green, right? That's our center of our partial negatives, center of our partial positives. We connect the two to draw our dipole moment. There isn't any, right? Because they're on top of each other. So this is a graphic. It's more of a visual way of representing how to calculate dipole moment, saying whether there's a net instead of this arbitrary thing moving around in space.
So if you were to word it, would you say also that it's like on the carbon, the partial negative charge?
Correct. The partial negative is centered on that central atom of carbon.
Okay.
Yeah, that seems very reasonable. Don't show. So, question number 3. Have you guys gotten an answer to this question yet? Do you need a minute? All right. Can we hear from Colin? Why does OCF then have a dipole moment?
Because O is more electronegative than S.
Okay.
Don't cancel each other out.
Okay, so let's start even one level higher. So what does the structure look like?
It's still linear.
Great. So because oxygen and sulfur are right over each other, then we know they're going to have similar properties. When we draw the molecule, we can even just say, well, I'm pretty sure the molecule is going to look like this. We can then go through and make sure the Lewis structure is appropriate. So we then have two polar bonds. But if we're doing their approach that they were doing, how does the difference in electronegativity you talked about between sulfur and oxygen influence and make it so that this has a dipole moment? Can you explain that a little bit more?
The center is no longer on carbon. It's closer to oxygen. So when you draw the line from
The center of what?
the center of the negativity is closer to oxygen.
Great. So the center of the partial negative is now a little bit out to the right. What about the partial positive?
On carbon.
Still on carbon. So you have your two centers are now different. So now you do have a dipole moment. Is it going to be very large? Probably not so much, especially if we compare to like if we had fluorine on one side and hydrogen on the other. I know that's not a right molecule, but. Did you have a question?
Oh yeah, I was going to ask if it's like wrong to say.
Yes. Sorry.
If
Go ahead.
it's wrong to say that like the forces cancel each other when in CO2, for example.
Forces. What forces?
The partial.
So I want to be a little bit careful when we're talking about partial charges. It's not necessarily a force that's pulling. It's an uneven distribution of electron density. So it's like saying, I don't know a good analogy for this. There's more.
Sand in a balloon.
Say again?
Sand in a balloon.
On one side versus the other? Sure, that works. I'm visualizing the heat maps that they have of electron density in a molecule, which is kind of like sand in a balloon, right? There's more towards one side than the other, so there's more electron density here. So that means if something else is close to it, this is more attracted to a partial positive. But this interaction here is still a covalent bond. And so this is not like this. There's a distribution, I guess where I'm having trouble connecting and describing this is that how many electrons are here between these two? 2 bonds. Each bond has 2 electrons, so there's 4 electrons between there. One of the things we discussed this fall is how Lewis dot structures are great at helping us figure out what the molecular shape is, but they're terrible at actually describing where electrons are. They say that we have 4 electrons exactly in this space, and that there's one right there in space and one right there. Why is that so wrong? Why is that a huge limitation of this model?
Because
they don't keep moving, they keep moving.
the double bond would be like.
They keep moving. What else? We picture an electron, and you listen to anything in quantum, what would we think about the position of an electron?
Repelling? Is that what we're talking about?
Quantum all the time.
Yeah, me too.
They wouldn't want to be like, yeah.
Okay, so there is a repulsion, but can we know the location of an electron?
No.
Okay, so we can know the probability of finding in a specific location. And so the idea that we now understand how we understand where electrons exist is that there's a probability of finding them. They're between these 2 nucleuses, as Logan was talking about. A double bond is actually a sigma bond and a pi bond, and so there's 3 different spaces in which the electrons are found. They're just found a little bit more of the time closer to the more electronegative one. So it's not like a force where something's pulling very strongly on one side. It's just the electron density is further away from one atom, closer to the other. Not sure if that's the best way to describe that visual. Aaron?
So further along in the packet, it starts to talk about bond length, and that has to do with like the size of the electron cloud. So if you have an atom like fluorine that's pretty small because it holds its electrons more closely to the nucleus, wouldn't you say that it has a stronger attraction and like a stronger pull of its atoms towards the nucleus, of its electrons towards the nucleus?
Yes.
So I guess I'm not.
So the distinction I was trying to make is that while electrons are held in a geographic location, if you will, a space around a particular atom, when they're bonding, it's not like a constant tug of war where one atom is pulling and there's a constant force like a string, right? That if you cut it, it'll go snap. Does that make sense? So it's just a different way of looking at it. So yes, atoms do have a different amount of pull on the electrons, and that's why they are unevenly distributed, but it's not force. Like the partial, so I heard some people talking about, let's do an extreme example, right? HCl. You have a partial positive here, partial negative. I heard a lot of people trying to describe this is an attraction between this partial negative and this partial positive. These partial negative and positive are the result of the unequal distribution of electrons. They are not the attractive force. That's kind of the distinction I was hoping to make. So we'll be getting into the size as well, and it's a very complex system, so in some ways there's a lot of different ways we can describe things that get us to the right answer. We just need to have a mental model that works to describe what we find. Quick question?
Yeah, okay, so I knew that it wasn't like the attraction of those, but I kind of thought that because Cl wants to feel like it's last because it only needs one, that it would want that, so I thought it was kind of like attraction.
Well, so the point that you're making is in order to make this, there's a strong attraction, and that's between the electrons, the valence electrons of chlorine, and the one valence electron of hydrogen. That is this bond. That is the attraction. These are a result of that attraction being a little stronger towards one than the other. So these are not the attraction force. All right. So last part before I have you guys moving forward a little bit. If we talk about CCl4, why does that have a net dipole moment equal to 0? Can I hear from a new voice? Matt?
Because it's going to have 4 bonds that are distributed evenly in a 300 or in a bad word. It has 4 bonds that are all of equal magnitude, and they're pointing in directions that will cancel each other out.
So is this an accurate way to draw that?
Only because we know that that means tetrahedral.
I was giving Mo a hard time about this. So when we draw the Lewis structure, right, one of the limitations is it helps us figure out the molecular shape, but it doesn't show the molecular shape. So I would prefer, instead of drawing this, if maybe we drew instead we have the capability to draw that, right? So that shows that these 2 chlorine carbon bonds are in the plane of the paper. This one's coming out towards us, that one's going in the back as tetrahedral. If we drew, terrible. The first one I drew, I'm not going to draw it again. 50 people are looking at you, you just can't draw properly. If we drew the original one, we would also show that the center of the partial positives and partial negatives would be in the middle, but that would throw us off in a lot of the other things that we're trying to calculate. So I want you always thinking in 3 dimensions, even if we're drawing or talking about things in 2 dimensions. So Matt, going back to your explanation, the reason is because all 4 of those are equally distributed in space, those bonds. They're all polar, right? Polar bonds?
Equal magnitude.
So then why does it end up with a 0 dipole moment?
Because if you were to take any one of those bonds, as negative pointing towards chlorine, the sum of the other 3 partial positive bonds would cancel it out.
Okay, great. And does anyone want to add to that in the terminology we've been using for the last couple problems? Colin?
The center positive and negative are both on carbon.
Great. So the center of all the partial positives and the partial negatives is right in the middle. Both of them are on top of each other. You can't draw a dipole connecting those 2 because they're at the same place. What if one of those wasn't chlorine? What if one of those was hydrogen instead? Would that change things? Okay. So we can think about how that would change the center. So the way that this particular, everyone has a different model, kind of going back to what we were talking about. Everyone has a different model of how to describe things. As long as it helps you describe what actually is found, the empirical evidence, then that's great. And the way that Rick Moog, who wrote this activity, visualizes it, I think is a nice tool to kind of learn how that all fits together. All right. Go ahead and question 5. I think we have a few questions, right, before that? Oh, no, that is the next one. So go ahead and talk to your neighbor, and then click in your answer. Which one of these 2 has a larger dipole moment? Your question? Magnitude is the sign. Yeah. So, what is the magnitude of the feature? Pick one. So, what's the magnitude? So, magnitude that's all going to be the space. So the magnitude Alright, has everyone got a chance to cook it?
On one of these, I helped a student out by explaining something, and something that caught my mind. I didn't get any answers, but I just helped them. Something that caught my mind was one of the students told me that they did this by doing the difference in the charges and the electron activities. And do you do that, or do you just look at the that there's a difference, so it's gonna be polar, or do you calculate it to a certain amount?
It's a certain amount and then a range. So I'll talk about that in a minute.
But when I was helping the student out, I told him that is that here?
Which makes sense.
All right. Overwhelming number of people answered B. Can you justify it? I hear from a new voice. Can you justify it? Josh.
It looks longer.
True?
Simple.
Okay, so then how do we know if that's, maybe it's weaker when they're further apart, maybe it's bigger when they're further
None
apart.
of the information was given. That looks longer.
Okay, what is that?
There's an arrow.
Okay, what is the label on that arrow?
D2.
Okay, which variable is that?
Obviously, it's just
Okay, so this arrow is labeling the distance, and that might be an inverse relationship, or it might be a directly proportional relationship. So we want to make sure.
Shows the +1, -1, so that's equal. +1, -1, so their magnitudes are the same, right?
Great, absolutely. So the magnitude is part of the equation. So what is the entire equation that we're using?
Lambda is equal to Q times delta. E.
So that's mu. It is
Lambda.
lowercase mu. So the dipole moment is mu, like micro. What is Q? Q is the magnitude. What does that mean?
Size of the atom?
Is it the charges of the partial
Charge or partial charge? Are these partial or full charges? How is that a partial charge? Haven't you guys done two full electricities that are like 0.27 versus minus 0.27, right? Okay, that's what we call a full charge, and if it was +2, it'd be a full 2 charge. If it's a 0.5, that's a partial charge. So let's be careful with our terminology. Okay, so the magnitude is how non-zero are they? So even if you didn't know that definition, you know they're the same on the left and the right, was Josh's point. But here, the magnitude, what we would use for Q, would be 1. And both of them are 1, so that variable is irrelevant in determining which one is stronger of a dipole moment. Moed?
So I had a question about the formula itself. Generally, whenever you compare like two different forces of attraction, right? If you have a positive or a negative, or a partial positive and a partial negative, generally, whenever you increase their distance, the force of attraction between them gets weaker, right? So am I understanding the concept of dipole wrong? Because in the formula it says that a dipole moment is bigger whenever there's a bigger distance between the two different charges. So
That's true. What is the other factor, though?
the other factor is the magnitude of forces.
Okay, and the magnitude of forces is related to electronegativity.
Right.
And so the next couple questions are going to get us into kind of parsing out those two. So we'll come back to that in a minute. So out of these two, the one on the right has the larger dipole moment because according to the equation, we have a similar magnitude of both, and we have a larger distance between the two. All right, let's take a look at the second one then. A couple seconds to answer this one. And closing. In a second. All right, we have 41 responses. Looks good. Who wants to answer this one? Describe why. 50? Why?
The magnitude is bigger. That's partially negative or positive. The blind is bigger than
Okay, so the magnitudes are bigger in A, and what's the other major factor? And distance, what about the distance between the two? Okay, so just to be very explicit, the distance is the same in these. The other one, the magnitudes are the same. Okay, so we're kind of parsing apart those. So how much bigger do you expect the dipole moment to be for A than B?
some.
2 times, according to our equation, because it's twice the magnitude of charges. All right? And you never know what you're going to get. Usually my clicker base tells me, but I messed it up today, so it doesn't. All right, so let's go ahead and, before we actually get all the way down to those, we'll check back in, I think, after we finish question 6. If you guys have not already completed that, make sure you finish question 6. We'll talk about those 2 competing factors of size and of the magnitude. And then keep working ahead. Never stop, always keep working forward.
Yeah, right. That's not a bug.
Like, I know what you like, can you be
I see what you're saying, because they're able so I don't know why that's true. I'm thinking.
What's up, guys?
I think that's part of the okay, so what's there she's saying? It's not like 2
So, and the distance is
just must mean that.
Compared to Connor, I know that you sent me an email and I never got to it. It's been a bad week, but that is removable. I'm going to help you first.
Listen, I'm here to succeed this semester. I really am.
I really don't want to buy a reminder.
Okay.
different, how is it looked in negative
Well, like in the equation.
So what's which one is it?
Okay, so let's just talk through question number 6 before we have people all over the place. So which atom is bigger, fluorine or chlorine? Maggie, what did you answer? Chlorine is bigger? Why? Tyler, you want to help out? Okay, the definition of it's larger as a large atomic radius. We know our periodic trends, right? So the periodic trends that we learned in Gen Chem 1, smallest atoms, typically the top right corner, Gets bigger as you go down and to the left. Hopefully you can describe why based on the quantum atomic configuration of those atoms. What did you say, Kayla? No. Okay, no, I'm serious. I want you to be able to define why those trends exist. Also why the trends of electronegativity exist based on the size of the atom, how many shells are full, how many electrons they have, all those kinds of things. If you're not comfortable with that, I'll be setting up office hours after tonight. Once all of you have completed a doodle poll, I'll try to find office hours at work, and then we can sit down and chat about that. Because in my mind, that defines all you'll need to know for organic chemistry. So if you'll be taking that class and you aren't comfortable with the atomic trends, we should work on that now so you're really strong when you get there. Okay, so then which has a longer bond, HF or HCl? New voice. Can I have someone volunteer? Logan.
I said HCl because HF, like fluorine being more electronegative.
Whoa.
More like pool.
You skipped the super obvious thing right in front of you and you went to much more complicated. Okay? So just with what we answered, how can we use that to define which one has a longer bond? Aaron?
Well, so we know that fluorine is going to have a bigger electron shell, so we know that it's going to have a longer bond.
Great. So you have hydrogen, and you have chlorine, hydrogen, and you have fluorine. The bond length is, how far is it from the center of those two atoms? That's a bond length. So one of those has a much longer bond than the other. HCl has a longer bond than HF. And then it asks next, which has the greater partial charge? F in HF or Cl in HCl? So we're teasing those two things apart. We're talking differently about partial charges versus electronegativity differences. Sarah, which one has a greater partial charge?
Fluorine.
Because? Much more electronegative than chlorine. Alright, so then the last part of this question is, why is the dipole moment for HF larger than the dipole moment for HCl? Have you guys got a chance to think through this yet? With those pieces of information? Raise your hand if you want 30 seconds to talk to your neighbor about why. Okay, not many people, so I'll just cold call. Can we hear from I can't remember your name. Corbin. Shoot, sorry.
I would just say, just kind of like referring back, like fluorine has a greater electronegativity than, hydrogen and fluorine together than HCl, so I just think that F would like push the H much more than the Cl would.
Okay, so I think the question's getting at, as well as like what is the electronegativity difference, what is more important to determine the dipole moment? If you guys go back, flip back to the last page, there's a table of the dipole moments. Did you guys check that out when you answered this question? Lynn, can you give me your thoughts?
So it like lists from HF to HI, it goes down that column, and
What does?
the table,
What column in the table?
molecule, starts with HF, well H2, but if you look at the HF, HCl, HBr, HI, just look at those and look at the dipole moment.
Great.
It drops while those molecules are getting larger on that trend. So that suggests that even though the distance is getting greater, the magnitude at which that charge is at is more important to the dipole moment's actual number.
You're going to follow?
Yes.
Very good explanation. Okay, so we have two competing things. We have the bond length increasing as you go down that table. We have the electronegativity values decreasing down that table. So Lynn's point is that the difference in electronegativity, the partial charge, is much more important when we look at dipole moment. All right, fantastic. Go ahead and complete question 7, and then we're going to have you do exercise 1, 2, and 3 we're going to start to do together. You're going to need to be thinking about the shape of these molecules. I guess we just answered question 7, right?
Yeah.
Well done.
Are you sure about
That's a very good question. So a lot of times we'll draw a double It's just kind of implied type of thinking as opposed to actually drawn out, but it is implied. That's right.
Okay.
So yeah.
Okay.
You're welcome. what do you think about this? This is the bigger one. So in this case, it's really more of the bigger trees. The lower is the turns around, right? In that case, it's right. You guys doing okay?
Yeah.
Yes, okay, okay.
And then I got further. Yeah, I got this is 2
Everyone here.
This is the longer, stronger.
That's all I know.
You want to answer questions?
You just made me sure.
That's a weird one, right?
So if you take out that, right, so this is Those important things to be able to use That's how they're. All right, so let's go ahead and work through some of these questions for exercise 3, I think it is. So the following molecules, I'm going to bring them up one at a time. I want you to click in whether they are polar or non-polar. And the letters are up there. I said it backwards. So go ahead and click in for O2. Pterodactyl. Refresh. 34. So I think there's two main steps I want you thinking about how to answer these questions to make it more efficient, faster. First one is, are there any partial charges in the molecule? For this molecule, what do we say? Are there partial charges, yes or no? No. Why? So it might be because of the shape, but we can also say it's the same atom, so there's no difference in electronegativity, right? So we can just stop there. We don't have to say, well, is the center of the partial positives on top of the center for the partial negatives, in which case it's, right? We don't need to do any of that. We can just say straight up that no, this is not a polar molecule. All right? I2. What about that one? Click on your answers. Jason, what did you say for this one, for I2?
So non-polar.
Why?
Same reason as O2.
All right, almost everyone agreed with you. Same reason, same atom, no difference in electronegativity. It's a long bond, but there's still no difference in electronegativity, so there's no partials. All right, what about CO? Go ahead and click in your response for that. Can I hear from Chelsea? What did you guys say? What did your group say for this molecule? Why? Okay, so oxygen is more electronegative than carbon, and there's only one bond, it's diatomic. So the partial negatives and positives don't overlap. All right, what about, let's skip water. You know water's polar, right?
Now I do.
Carbonate. And one of these reminders, if you don't remember all of your polyatomic ions, you will need to. This semester is going to be full of using polyatomic ions. You will need to have those memorized and know the formulas. A couple more seconds. Ooh! So why are we mixed on this one? Lauren, do you want to share your group's thoughts on this, since you were raising your hand? Austin?
So, like, shouldn't the bond length on one of the carbon and oxygen bonds be, like, shorter because it's one double bond versus two single bonds? Which would affect the...
It's a great question. So the first thing you might have done to get to that point is? Did everyone draw the Lewis structure?
Yes.
Okay. You have two negatives. We put a whole bunch of lone pairs. What do we think? Do we agree with Austin that one of those is shorter and hence offsets where the partial positives and partial negatives are? No! Sorry, Austin, really. What are we missing? What is resonance structures? Okay? One of the other limitations of Lewis structures is you can't draw the actual molecule. If you go with X-ray crystallography, we can actually see where the atoms are placed next to each other. We find that all three of these oxygens are equally spaced away from that carbon. So this one drawing is not accurate to show us what the structure of that molecule is. We have to draw the two other resonance structures. And which one of those three is it? None of them. It's an average of all three, where all those bonds are the same length, the same strength. So that is a nonpolar molecule. What about the last one? Polar, nonpolar? Last question. Almost everyone is saying that this molecule is polar. Why? Are there any partial positives or partial negatives? There's not, because carbon and hydrogen are the same, right? Except for carbon chlorine. Partial negative, partial positive. Those two don't lay on top of each other. In the grand scheme of things, that molecule has a relatively small dipole moment because there are so many nonpolar bonds in that molecule. The rest of this packet, you guys are capable of doing on your own. This is great practice to make sure you're doing what you're supposed to be doing and understanding it. It gets a little more complex, but you have all the tools. There's a pre-quiz for Wednesday on OWL. Make sure you complete that. And I will see you guys in class on Wednesday. I'll send an announcement with office hours. And if you are subscribing to OWL and you get a thing saying it's going to expire, it won't. If you paid, if you've registered, you're fine. It'll just say 4 days, 3 days, and then it'll go away. Sorry, Ruby.